the risk factors will significantly increase compared to if you are in the same countries. Do the same countries understand this, or is there a problem? No. Okay. Radioactive decay is considered a stochastic process, meaning it is an unpredictable process. You cannot determine which atom will decay. For example, if you have a material with 1,000,000 atoms, you can identify which atoms will undergo decay, but you cannot specify exactly which atom will decay. That's why it is called a stochastic process. Now we talked about activity. We are discussing decay rate, becquerel, megabecquerel, and gigabecquerel. 1 unit is 10 to the power of 9 becquerel. The unit Curie, and 1 millicurie is approximately equal to 37 megabecquerel. Doctors, are we tired or should we continue?
No, I'm not tired. I'm fine with you all.
Doctor, if you please, could you explain more about electron capture?
Welcome to the social tower media pages.
Why does electron capture occur? It's not just beta emission. Both happen, doctor. Both occur, but with heavy atoms that have a high atomic number. What does a high atomic number mean? It means a high number of protons inside the nucleus, which initiates electron capture. This process attracts an electron from the shell. Both processes compete with each other, but the probability of electron capture increases with heavy atoms or heavy materials that have a high Z. Now, if I have radioactive material like this and I bring a detection device, you all have seen the survey meter, which is the device that measures radiation. You start by detecting the gamma photons that are emitted from the radioactive material. So, what does that mean? It means that I am detecting gamma photons. And here is the radioactive material. And here is a photon. Each photon interacts with the detector and gives you a count, telling you that you have 1,000 counts per second. What does 1,000 counts mean? It means that 1,000 photons reached the detector and were detected. So, the count here represents the number of photons coming towards the detector. However, the radioactive material emits gamma photons in all directions. Everyone. So, the detector that detected the gamma photon is related to the detection that occurred, or the count rate, which is the counts per second. There is a satisfactory relationship between it and the activity of the radioactive material, but it does not equal the activity, which is understood. Why? Because it measures in only one direction. The radioactive material is isotropic. It emits radiation in all directions, in a circular shape, while you are standing with your detector. This detector only measures the radioactive material coming from that direction. In a circular shape, unlike X-rays, we all perform calibration for it. No, the radioactive material emits radiation from all directions, just like from the front, back, and above. Every part of it emits radiation. So, does the count that I detected represent the activity of the radioactive material? No. It increases with the increase in the activity of the radioactive material, showing an indirect proportionality with the agreement. Why do you keep saying counts per second? Because the term counts per second will be frequently mentioned in the upcoming period. The gamma camera detector. And here is the patient with the radioactive material. Your gamma camera or your aspect detects the count or the gamma photon coming in and represents it to you in counts per second. When you tell your machine during acquisition that you want it to detect 1,000 counts per second, or 2,000 counts, or 1,000,000 counts, or 2,000,000 counts from this patient, the machine will remain focused on a specific area of the patient to take the image until it provides the pre-adjusted counts that you requested. So the count here is considered an acquisition parameter that we will use in the upcoming period. How many counts you take. Here. No, that's it. It is considered. We will use it. During the upcoming period, how many counts are you getting? From the image, from the detection, from the view, or from the position? Okay, doctors? Okay. They say that when radioactive material or activity undergoes decay, it follows something called exponential decay, which takes this form. The term exponential contrasts with linear. When I say there is a linear relationship, it means it takes a linear shape, while exponential means it follows the exponential function. The exponential function does not reach zero. It continues like this, without reaching it, but the linear function does reach zero. The decay of radioactive material practically never reaches zero. The activity of the radioactive material, if you assume your activity is 100 millicuries, and you want to find the activity after a certain time, the activity at a specific time t equals a node multiplied by the original activity, which is the original value, in e to the power of Lt. Here, L is called the decay constant, which is not our main topic, but I want to show you through this equation that E, which is the exponential, is fundamental, is the exponential decay represents the decay of our radioactive material. Here, it is referred to as a logarithmic curve. What does logarithmic scale mean? It means that the equation, which looks like this, can be transformed into a linear form by using something called logarithmic scale, which will show up as a straight line. This is a mathematical concept, but you need to understand that the decay of radioactive material is considered exponential decay, or follows the exponential law. We said that there is biological half-life and physical half-life. What is the physical half-life? It is a characteristic of the radioactive isotope itself and is not related to anything biological. The radioactive material in the human body is excreted through urine and other means. There is something that accelerates the washing out of the radioactive material from the human body. So, both biological and physical half-lives are related, and they give you something called the effective half-life. The effective half-life is calculated as 1 over the biological half-life, meaning that the effective half-life will always be less than the lesser of the two. For example, if the biological half-life is 2 hours and the physical half-life is 6 hours, the effective half-life will be less than 2 hours according to the equation. Now, if we talk about the production of radioisotopes, let's focus together. I now understand the idea, the isotope, and the decay method. Let's get to work and see how we can produce the radioisotope and inject it into the patient. I have 3 sources for radioisotope production: cyclotron, nuclear reactor, and radionuclide generator. Surely, you are familiar with the cyclotron or nuclear reactor and radionuclide generator. So, let's design the cyclotron. What is the idea behind the cyclotron? The cyclotron is used in the production of fluorine-18, which is used in PET scans. They will tell you that if you want to have a PET scan, You need to get the fluorine 18 from the nearest place because its half-life is 2 hours or even 10 minutes. So you need to have a cyclotron nearby. Back in 2009, there was no cyclotron in Egypt, so we used to get the fluorine 18 from Turkey by plane. For example, we would get enough for 2 or 3 patients because the fluorine 18 would come from Turkey by air. The flight from Egypt to Turkey takes about 3 hours. If I want the radioactive material to arrive at the center at 50 millicuries, it must leave Turkey with more than double that amount to account for the 3-hour journey. So, if we say the flight takes 2 hours, it must leave the airport with 100 to reach us at 50, which is under the best circumstances. So, we would be preparing this material to come from Turkey just in time to inject it into 2 patients or so. This is why having a cyclotron is very important for producing a range of radioisotopes used today in PET scans, especially fluorine 18. The basic idea of the cyclotron is that I bring a particle or proton and I accelerate it. What does acceleration mean? It means giving it energy. The more energy I give it, the faster it moves. When it reaches a certain energy level, it starts colliding with a target. For me, if I want to produce FDG, this target is oxygen, and this water contains oxygen. So why do you want to do this? Simply put, weren't we saying that the radioactive substance needs to have an imbalance in the number of protons and neutrons to be stable, right? Also, I know that I separated it, but please focus on the following case. So if I want to create a radioactive substance, I need to create an imbalance, right? Sure, that's the idea. To create an imbalance in the substance you have, or to activate it so that it transforms into a substance of emotions. So what happens is that you have a substance like oxygen, which is supplied with a number of protons inside it, leading to an unbalance in the number of protons relative to the neutrons. This transforms oxygen into a state where oxygen 18 gives you fluorine. Then you take the fluorine, use it, and attach it to glucose, labeling it with glucose, and then I start using it as FDG. Do you understand the idea? So, the idea of the cyclotron, or the idea of a nuclear reactor, is that you manipulate the imbalance or change the balance between protons and neutrons. When you change the balance between protons and neutrons, you make your material activated, you make it more active, you make it unstable, so it reaches stability by providing you with the daughter isotope you want, the radioactive isotope you will work with. Do we understand the idea? How does all this happen in the cyclotron? In the cyclotron, I have protons, and I apply a strong oxidation force to them. This force is necessary to give them a certain energy that allows them to collide with the oxygen 18 present in the water that I will use as a target, affecting the unbalance or changing the balance between protons and neutrons. So how does this happen? First, you use 2 electrodes, the orange and blue ones. These are 2 electrodes, one positive and the other negative. I connect one to a negative electrode, as we discussed before regarding the positive and negative electrodes, which provide an electric field. One is positive and the other is negative. I will call them 2 Ds. Why Ds? Because they form the letter D, so D1 and D2. The charge always moves from the positive to the negative, from the positive to the negative. Now, I will make this electric field alternating, meaning it changes. Sometimes the positive will be negative, and sometimes the negative will be positive. I will tell you why in a little while. He placed above the 2D diagram and said that the magnetic field is a magnetic field. I will also use this magnetic field for a specific purpose shortly. Therefore, the magnetic field is perpendicular to the electric field. The electric field runs from positive to negative, while the magnetic field is perpendicular to the electric field. Up to this point, I think things are clear. It starts by placing the proton inside the electric field. As soon as the proton, which has a positive charge, is placed, it moves from the positive to the negative. Now look, I placed the proton here. What will happen? This proton, due to the electric field, will be given kinetic energy, telling it to move from this positive place to the negative. It will be given a force, a push. All right? See how the electric field gave it a force? Now move. May God be pleased with you from the positive side. So it was given acceleration. This force caused it to accelerate. All right, look, it entered the negative. As soon as it reaches the negative, it has reached a state of rest. It won't move again. So what will happen? They said there is a magnetic field. Remember, it is vertical above. This positive charge is considered to be accompanied by a magnetic field. Any charge in the world is accompanied by a magnetic field. The existing vertical magnetic field changes the direction of the electric field, as if it is creating a semicircle, as if it is rotating. So the movement of this electron is a result of the effect of the magnetic field on the electron. Then it starts to return to the surface of D2. Now, I want it to complete the rotation. So what does it do to complete its rotation? It changes the polarity, making the positive charge where the negative was. Look, it reaches here and stops, making this blue one positive, giving kinetic energy to the positive charge that is coming from acceleration, increasing its speed and expanding its diameter, creating a larger circular path. So, it will start to move in a wider circle with a larger diameter. And this diameter depends on the acceleration from the kinetic energy resulting from the electric field. Look, it's like you're accelerating and charging your protons. All right, that's the end of the video. Look, until no, but Mohammed, the polarity changes. This was positive, then it becomes negative, so it can move. It reaches here, it completes a turn. With the magnetic field changing this positive again to continue its rotation. This is because if you look, this is now positive, it moves here, stops, and has reached its place. It changes with the magnetic field, reflects the polarity, and moves again with the magnetic field and the electric field to complete the turn. Okay. He continues to meticulously and carefully complete the intricate and complex process until he reaches a specific stage where he successfully and completely finishes the entire diameter. At this crucial and important point, he has effectively and efficiently created a very high level of energy, which is significant for the subsequent steps. Then, he reaches a particular stage where he exits the process and meets his predetermined and specific target. This target, in our specific case, is the transformation of the target material, which is the isotope oxygen-18. It is precisely and accurately hit by a proton, resulting in the formation of fluorine. This transformation is crucial as it highlights the change in atomic structure. Now, both oxygen-18 and fluorine have the same mass number, but they differ significantly and notably in their atomic numbers. This difference raises an important question. Can I indeed separate them chemically or not? The answer to this question has profound implications for the field of chemistry and material science. You can separate them, but this is what will happen. When you extract the material containing oxygen 18 and fluorine due to the difference in atomic numbers, you have managed to separate them. At that time, you can take the fluorine and work on its process to prepare fluorodeoxyglucose or fluorodeoxy, and so on. Is that clear? That's the cyclotron, right? There are some other things that come out with the cyclotron, such as gallium-67 and thallium-201, and other elements. Gallium is used in inflammation, while thallium was used in cardiac imaging, but is not currently used now. The second thing is the nuclear reactor. What is a nuclear reactor? The nuclear reactor's function, in simple terms, is that we all hear about uranium. Uranium is considered a heavy material, meaning it has a high atomic number. If you expose it to neutrons, it undergoes a process called fission or nuclear fission. This nuclear fission results in the production of radioactive materials and generates a lot of energy. The radioactive materials that are produced undergo what is called a decay chain process. For example, I have uranium-235. I will hit it by bombarding it with neutrons to create a significant imbalance, resulting in something called uranium-236, which is a crucial step in the process. This uranium-236 will undergo a transformation and decay into a different element known as molybdenum. It is important to remember that molybdenum gives me technetium, which is a highly valuable element in nuclear science and is excellent. Consequently, I can use molybdenum in the nuclear reactor in a controlled environment through the fission reaction that I will carry out on uranium-235 in order to achieve the desired reaction, or I can obtain the regular, stable form of molybdenum, which is naturally occurring and not radioactive, and subject it to neutron bombardment to induce the necessary changes in the neutrons from the proton that is present inside, transforming it into molybdenum. Let's take a look at this and see what this structure is. This is a nuclear reactor. We will learn some secret information. First, you will find uranium. You will see the view you are looking at. What is this view? You will find something called a control rod, something called coolant, something called shielding, something called moderator, and something called uranium fuel. This is about the concept of shielding, which is what protects the nuclear reactor from the outside. It involves using a material, whether it's lead or a different material, with a certain thickness to prevent anything from leaking out of the reactor. Inside the nuclear reactor, there is uranium, specifically the uranium-235 that I was just talking about. And you have a source of neutrons, meaning something that gives you neutrons